So think back to geometry. You'll take your AirPods out if you don't mind. Think back to geometry when we were doing transformations and we talked about symmetry. For instance, if you had, I'm going to make it very simple, if you had, say, a triangle right here that was reflected over the y-axis to land over there, imagine those are perfectly the same. If I said to you, what is the line of symmetry, you would say that it was the y-axis, because you could take this picture and fold it on the y-axis and they would line up, the images. Do you remember that from geometry? Mine better. That's the same thing we're doing now, but we're leveling it up. We're doing the college level concept of symmetry. So we're going to look at graphs, just like in geometry, and just determine if they are symmetric, but then the level up aspect comes in being able to write the equation based on what type of symmetry they have. And then we're going to use the fancy vocab words, even, odd, or, of course, neither, to discuss the symmetry. So first, let's look at this slide right here. This is symmetry in nature. When am I ever going to use math? Well, you're not going to be walking down the road and asked to find symmetry. But if you are walking in nature, or even at the Taj Mahal, if you're at the Taj Mahal, maybe you can appreciate the symmetry that is in construction, engineering, and just nature itself. If you've ever looked at a snowflake under a microscope, it's really cool and has a lot of symmetry. That would be, the nature aspect of it. So from this slide here, what I want you to appreciate is that it's all around you. And then I want you to understand that sometimes even architectural buildings have symmetry, like right there, if I dropped a vertical line and folded that image, it would be symmetrical. Do you agree? Let's go to the next slide. Slide 3 of 11. Move it on up. Okay, look at this graph right here. This is a quadratic that has been turned on its side. That's because it's if you look, we're used to y equals x squared. This is x equals y squared. It is the inverse equation. So consider the points 4, 2, and 4, negative 2. Points like these have the same x value but opposite y values, and that's because it's a reflection over the x-axis. If you think back to geometry, in geometry, if I said, what is the rule to reflect this image over the x-axis, you were supposed to, in geometry, say, okay, if it's reflecting over the x-axis, the image is going down or up. Would you agree? Which means, what's the only thing changing in the points? The sign of the y value. So the rule would be that the sign of the y value changes. This does not mean make it negative. This means negate it, which is like argue it, change it, opposite. So this means, I'm trying to draw an arrow. This means opposite sign, not make it negative. Okay. That is from geometry. So I'm going to put recall. This is from geometry. The rule of any standard point on the image, the pre-image, you would simply change the sign of y, and then that would reflect it over the x-axis. If I was reflecting over the y-axis, which is the next slide, I would change the sign of x. So what would the rule be without going to the next slide and looking? What would the rule be? Negative x, comma, y. Let's take some notes before we switch to the next slide. You are going to want to use Holcombe to help you find the lines of symmetry. If you don't remember how to use Holcombe, here's your refresher. Hoi stands for horizontal lines have a zero slope. The equation of those lines is always y equals whatever number it is touching on the y-axis. Okay? Vertical lines have an undefined slope. Their equations are x equals the x value it's touching on the x-axis. Okay? Paige, do you need notes? So looking right here, where is the line that I would fold it to make the image symmetrical? It's the x-axis. If you have a highlighter, highlight that, or if you have a colored pen, use a colored pen. It is symmetrical about the x-axis. What is the equation of the x-axis? Well, what direction does it run? It runs left to right, which is which one? Like, it's horizontal. So the equation is y equals where it's crossing the y-axis. It's crossing at 0. Okay, go to the next slide. We have not leveled it up yet. This is still geometry. The level up aspect comes when I throw the functions at you. All right, the next slide. Notice this time the quadratic is facing up. Look at these 2 points here, for instance. 3, 4 and negative 3, 4. Recall from geometry, if the pre-image is xy and you're reflecting over the, what are we reflecting over here? The y-axis. This is symmetrical about the y-axis. You'll notice we're writing the same things, but we're writing it based on this picture. So let's use Holcombe. What's the equation of the y-axis? X equals 0. So it's a vertical line, which tells me it's going to be x equals a number. You go to it and you see where it's crossing the x-axis, that's the number. So it's going to be x equals 0. It's not enough to say it's symmetrical over the y-axis. You need to be able to say which is the equation of the line x equals 0. Recall from geometry, if it's reflecting over the y-axis, what is changing? Just the sign of the x coordinate, right? So this would be negative x, comma y is the rule that you should recall from geometry. And remember, just like I put on the last slide, The negative does not mean make it negative. It means opposite sign. Now there is one new symmetry. That's not new, excuse me. It was called something specific in geometry. We are not using that vocab word here. It is rotating 180 degrees around the origin. Everybody good with this slide? Almost. So these first 5 slides are reminding you of standards from geometry, and then the last slides, the remaining 6 slides, are where we're doing the leveled up aspect of it. This slide is showing you there is a symmetry that is 180 degrees around the origin. So, like, focus on my paper. It's a rectangle, right? Look at the orientation of it. So if I rotate it 90, is it symmetrical? If I rotate it 90, to the original image. So here's the image, right? If I rotate it 90, it changed. So if I rotate it 180, it lands right back in the shape that it was. Now I know that it's upside down, but that's not what matters. What matters is it's landing in the same shape. So that would make it symmetrical. From geometry, I'm going to put recall, it was called point symmetry. It was called point symmetry because basically you held your finger down on a point, which was the origin, and you rotated it 180, and if the image landed in the same shape, it was symmetrical around the origin by 180 degrees. You may not remember that one from geometry because it doesn't come up a lot. Because if you think about it, there's not a lot of shapes that you can do that to. Like if I have a quadratic, right, can I rotate it 180 and it land right back like this? No. If I rotate this 180, it's going to now be opening down. I'm trying to think, linear. If you take a line and you rotate it 180, it's going to, the slope went from, it might be positive, it would switch to negative. So there's not a lot of examples of this. Let's take some notes. Here's a rational expression. Let's say for any xy, we're going to just put right here xy. If you rotate 180 degrees, rotate 180 degrees. Now this part you should remember from geometry. Your rule for rotating 180 is opposite x, opposite y. Opposite x, opposite y. That means change the sign of both of the point numbers. I don't know if you remember this from geometry, so I'm going to see if you do. Okay, imagine, so in geometry, you were supposed to memorize the rotation rules. You were supposed to memorize them. If you had me, I told you don't memorize them because they're very complicated and they're very tedious and you could easily mess them up. So my geometry students, I showed them, which this was magnetic, I showed them this Post-it note concept that I found on YouTube. I wish I could take credit for this, but I can't. Someone else did it. What type of numbers are to the right? Up, left, down. Okay. This Post-it note technique helped generate all of the rules for rotations without memorizing a single thing. The way it works is you imagine an X and a Y axis labeled, always has to be the positive ones, by the way. And then you rotate the Post-it note however it tells you to. By the way, does it matter on direction when I rotate 180? Does not matter. I can go that way 180 or I could go that way 180. I still land in the same direction. So if I'm rotating 180, that's 2 turns with my rectangle, correct? So that's 90 and that's 180. Do you agree? Then you read the Post-it note to get the rule. You always read the horizontal first. It would be negative X, negative Y, which is the rule for rotating 180. Now, just to show you in perspective, this is not going to happen with us. If I rotated 90 clockwise, the rule would be positive Y, negative X, which means they had switched. So to help you understand how that works. So this rule is from geometry that you already know. And I'm just reminding you of where it comes from. If you rotate 180 degrees around the origin, this is the center of rotation. This is where you hold your pencil down, which is why I call it point. It's called point symmetry. You hold it down and you spin it 180, and it lands in the same place as it started. It has point symmetry. It is symmetrical with respect to the origin. Symmetrical with respect to the origin. Which means the only thing that stayed still was the origin as you spun the image. Okay, that was a refresh from geometry. Now let's level it up to college algebra. We're going to look at the exact same things that we just did, but now we're looking at it in terms of the function. You will be happy to know there is not a single domain question in here. Yay! Okay. Algebraic test of symmetry. Let's fix this box because this is going to be helpful for you. Okay, good. Sorry, I just panicked because I saw that over there. Let's fix this box so it's helpful because right now it's all blurred together, I'm sure. There's 3 types of symmetry we just discussed. There's over the x-axis, over the y-axis, or around the origin. To determine if a function is symmetrical over the x-axis, if you think about it, the x runs this way. That means it's flipping up or down, which means what's changing? The y is changing. To determine it algebraically, without looking at the graph, without graphing it, you simply replace y with negative y, and you see if what you get is the same function than what you started with. Because if it is, then it's symmetrical over the x-axis. So I want you to underline right here where it's telling you what to do. Or highlight, it's up to you. I think if I highlight, oh, well, you can see it. All right. To test algebraically if it's symmetrical over the y-axis, so that's right and left, correct? Which means what's changing? X is changing. You simply plug negative x in, and you look and see if it's the same equation as what you started with. To check if it's symmetrical around the origin, which is that point symmetry, you have to go back and think of the rule from geometry, the rule was negative x, negative y. Plug both negative x and negative y in and see if the equation you get is the same as what you started with. And if it is, it's symmetrical around the origin. Okay. Let's dive into an example. Test y equals x squared plus 2 for symmetry with respect to x, y, and origin, which means we have 3 things to check here, right? And our equation is y equals x squared plus 2. This is how I'm going to organize mine. First of all, I'm going to go to a thinner pen because you're not going to be able to, I'm not going to be able to fit it all in. I'm going to organize it by saying my work for the x-axis will be here, for the y-axis will be here, and the origin will be here. For this exam, you will have to memorize what to plug in to check for which one. Which means you're going to have to practice this so that you have it memorized, or make 3 flashcards. Flashcards really do work. And honestly, the process of making the flashcards sometimes is all you need. Like, you don't actually have to sit there and do the, like, just writing it down on the flashcard helps commit to memory the rule. If I'm going over the x-axis, that's flipping up or down, so what's changing? The y. So you're going to take y and replace it with negative y, and you're going to see if your equation matches what you started with. So what did we start with? Y equals x squared plus 2. Where there's y, I'm going to put what? Negative y. Okay, so that right there, y equals x squared plus 2. I'm now going to write negative y. I'm trying to make it bold so you understand that that's me plugging it in. Equals x squared plus 2. Now solve for y. Get y by itself. Subtract or divide by the negative, right? If I divide by negative, what happens? To the stuff on the other side. Everything changes sign. So is this equation the same as that one? No. So no, this is not symmetrical over the x-axis. It's so simple, it probably makes you think you're doing it wrong. Like, because you're just plugging it in and you're looking at it to the other equation. Now let's do the y-axis. Okay, so you got to think, y-axis runs up and down, so that means it's flipping right or left. So what's changing? The x is changing. So where there's x, I'm going to replace it with negative x. So my equation is y equals, there's an x. I'm putting in a negative x. I'm putting it in parentheses because it's attached to an exponent. Squared plus 2. You make this bold. Now, if there's anything to clean up, clean it up. What's negative x times negative x? Bless you. Isn't that x squared? Does everyone agree? Is that the same? Yes. Is that the same equation that I started with? Yes. No, because what's negative x times negative x? Positive x squared, right? Now, origin, go back to geometry, think of the rule. The rule is xy becomes negative x, negative y. So you're going to replace negative x in the x and negative y in the y. And I am running out of room. I guess I can make that box smaller. Okay, so negative y equals, here we go, negative x squared plus 2. So this negative y comes down, this becomes x squared plus 2. It's going to be the same as when we were checking, what is it, the x-axis. Divide by negative, and we do not have the same equation. I put the graph on here so that you can see the visual. This was the graph of what we just looked at. Now you can see that it definitely does not flip over the x-axis and line up. You can't fold it over the x-axis. You definitely can fold it over the y-axis. You also can see that you definitely cannot rotate it 180 and it be the same. All right. Well, a quadratic that is facing up or down won't be symmetrical over the x. That's what we're, if you look right here, we did that one. Yeah. Now that, if that's not a function, in order to keep it symmetrical, it does have, you do have to say it's no longer a function. To talk about symmetry over the x-axis. All right, go to this one. This is a practice problem. You do it. You're testing x squared plus y to the 4th equals 5. You're testing it for all three. Yeah. So you're just checking the algebra. Remind yourself of the rules, and that you'll notice they're opposite of what you're checking with. You're checking over the x, it's the y that changes you're checking over the y, it's the x that changes. This is to see if you remember the rules of your exponents, like with negatives. Negatives plugged into even powers produce positives every time. Negatives plugged into odd powers produce negatives every time. So that's kind of a quick way to look at it, like a snapshot. You got an even x squared, you got an even y to the fourth. So that's your clue that this is probably going to clean up nice when you go to plug these negatives in. So here I'm plugging in negative y. So we got x squared plus negative y going into parentheses because it's attached to an exponent equals 5. It's an even power, so it's going to come out positive. So this just becomes y to the fourth. What? We're not solving, you're just checking to see if the equation is the same as what it started as. And you don't want to change the form because the one it started as was the x and the y's were over here to the powers. It has to be the exact same. Same power, same sign. Alright, so this matches, right? So the answer is yes. Okay, now let's check the symmetry over the y-axis. So you've got negative being raised to an even power. That would become positive. Same equation, right? So, yes. Now I'm going to say something that don't run like through the fields screaming it. I have never found a function that if it's yes, then no. I've not come across one of those yet. So if you're getting yes and yes, do not say, oh, well then by default it's got to be yes. You need to check it because what if you messed up on one of these? When you go down here to do this, if you messed up somewhere, then they should not match. Something should be off, okay? So don't look for a cop-out to not do the work. Go ahead and do the same thing here. So we've got x, sorry, I was trying to plug color coordinate. We've got beep squared plus beep to the fourth equals 5. We're plugging in negative x and negative y. So once again, they're raised to even powers. They should come out positive. And that is the exact same that I started with. So yes, it's symmetrical around the origin. How do you feel about checking the algebraic symmetry? You're going to have to memorize this part. So I don't know if you want to highlight it or put like a big asterisk to say when you're studying. You're going to have to know if you're checking for symmetry over the x, plug negative y in. If you're checking for symmetry over the y, plug negative x in. If you're checking for symmetry around the origin, plug negative x, negative y in. You will have to memorize that. But if you think of what's actually happening, like flipping a paper, then you could deduce it. Or if you just remember that they're fast backwards, right? If I'm checking over the x, I'm changing the y. If I'm checking over the y, I'm changing the x, and then you have to just remember the origins of both of them. Okay. 3 slides left. Well, 4, technically. Now we're looking at the words even and odd in terms of symmetry. Let's take some notes here. All of these here were plain equations, right? If you look back at all of the examples we've done, it was y equals something, correct? And you even said how can you have like symmetry over the x-axis, right? Now we're going to look at what word has changed. We're now looking at functions. We're no longer just talking about y equals something. Now we're talking about the whole like f of x. So where we used to have a y, now we have f of x. And it's passing the, remember what it's called? Vertical line test. So, for instance, it's gone. Okay, I fixed it. And I'm still recording. We're good. So, for instance, right here, let's sketch the mother function, parabola. This is f of x equals x squared. Is that symmetrical over the x-axis? If I fold it over the x-axis, do I end up with the same imprint? No. If I rotate it 180 degrees around the origin, do I end up with the same imprint? If I rotate it? No. It would end up being up here, and now it would be down here, right? Is it symmetrical over the y-axis? Yes. Let's take some notes in this box. This box is where you get all of your most important info, but when you first look at it like that, you probably can't decipher what it's saying. We're learning 2 new vocab words. Even function, odd function. And no, it has nothing to do with the numbers being even or odd. If it's an even function, it means it is symmetric with respect to the y. It is symmetric with respect to the y. If it's an odd symmetry, it's symmetric with respect to the origin. Which symmetry did I not say? The x-axis. That's because any graph that's symmetric to the x-axis will not pass the vertical line test, which means it will not be a function, and we are only now discussing functions. So if I'm talking about equations, you're just checking, and that means you see the letter y. That's how you know. I'm talking about equations. you're just checking the algebra, right? If I'm talking about functions, then you can only talk about the y-axis or the rotation around the origin, because over the x-axis would mean it's not a function. How are you going to memorize that even is with respect to the y and odd is with respect to the origin? Take some notes right here. An even, don't write real big, let's see. You need 3 lines. You need space to write 3 things. An even function is symmetric. I'm going to draw an arrow to say, like, an even function refers to symmetry around the y-axis. So y-axis symmetry. If it's even symmetry, it's symmetric around the y-axis. Now, go back to the last couple of slides. If it's reflecting over the y, what changes? The x changes. This means that if you take and plug, what in? Go back to the last slide. If we're checking over the y-axis, we plug what in? Negative x in. So if you plug negative x in, and it comes out to be the same equation as the original, then it's symmetrical. Now, these are written backwards up here. So I'm gonna, there's 2 ways to write this, because it is an equation, which means it doesn't matter how you write it. The way that I just wrote it is telling you how to check it. Plug negative x into the function and look and see if it's the same as the original. That's how you check it. Okay? Up here, you'll notice they have it reversed. They're saying, hey, take the original, then check and see if it's the same as what you get when you plug negative x in. It doesn't matter which way you write this. They mean the same thing. And I'm going to show you how to do it in the next slide. Odd function. If you have an odd function, it means that it has an origin symmetry, which means you're turning the image 180 degrees, holding your pencil down on the origin. The algebraic way to check this, if you go back to the last couple of slides, when we were checking the origin, we plugged both negative x and negative y in, right? Okay, but since we're talking about a function, we have to be able to represent it in one little simple equation. So the way that it's represented is, take the function, plug negative x in, which you're going to do that when you check for even. So that's already going to be done. And then check and see if it's the same thing as negative f of x. Now, why does this say negative f of x? What is f of x equal to? Y. Okay, so this is saying plug negative x in and see if it produces negative y, because the rule for checking around the origin is negative x and negative y have to be plugged in, right? Let's make a small note. There's no name for x-axis symmetry, I'm abbreviating, because it's not a function. Now, how are you going to memorize this stuff? I have a stupid, corny way to do it that works for me. Hopefully it'll help you. It has to do with the odd one. Where do you think I'm going with this? Odd origin. Odd and origin start with O. So the way I memorize this is that if it's odd, it has to rotate around the origin, which means both x and y's have to be able to be negative and it be the same function. I'll show you the algebra part on the next slide. Even, the way I remember even is I go back to this mother function right here. That's really bad. I go to this mother function right here because I always tell myself this is a parabola, a quadratic, which is x to the second power, and that's what type of number? Even. So I always tell myself, think of a quadratic, the quadratic, the mother function quadratic. It's symmetrical over the y-axis, and it's an even power. So that's how I tell myself, if it asks me to check if it's an even function, I'm checking with symmetry to the y, which means I'm plugging negative x in. Okay? All right, that's how you're going to memorize that stuff. Now let's actually look at the algebra. We have three practice problems for this, and then we're done. Okay, determine whether each of the following functions is even, odd, or neither. It sounds like you're finding three things, doesn't it? Well, good, because you're not. You're just finding two, and if both of them are no, then it's neither. Let's organize our thoughts. We're going to check if it's an even. Always check even first. There's a reason for it. I'll tell you why in a minute. Huh? Okay, you are going to have to memorize what I'm about to write. If I'm checking if it's even, this is where your thought process, what I'm about to say, is what your mind should say to yourself when you're doing the homework and doing the exam. If I'm checking for even, that's that mother function in the corner. Hopefully this will help you remember. It was a parabola, which means it's what power? It's the power of 2. That's why it's an even number. So I'm checking to see if it's symmetrical over the y-axis, which means a right and a left flip. And that means what changes? The x. So we're going to copy the formula. F of x equals f of negative x. That's the formula that you're copying. You're saying take the function and check it after I plug negative x in, right? Now, change to a colored pen or a highlighter or something. Here's where I found people get confused. This is what you're doing. So I want you to write, do this. I found that people get confused when they see this. They think they're doing like two things or they're dealing with two functions. You're doing one simple thing and you're going to the end of it and checking it to see if it matches this. So check with this. So we're going to do that and check our answer and see if it matches the original. Does that make sense? Okay, so f of negative x equals, so this means you're plugging negative x into that big function. So everywhere there's an x, beep it out. 5 beep, to the 7th minus 6 beep, cubed minus 2 beep. And now everywhere there was an x, I'm putting negative x. And now you're going to think of what Ms. Holcomb's already said to you. This is checking if you know the rules of your even and odd exponents. Do you know that if you have a negative value to an odd power, it's going to come out negative? If you have a negative value to an even power, it's going to come out positive. That's what it's checking. So like right here, this would end up being 5 times negative x to the 7th, because that would come out negative, correct? So that would be negative 5x to the 7th. This would come out what? Well, wait, look what I'm pointing to. Hold on. This would come out negative x cubed, and you would multiply it with negative 6. So be careful here. So that would be positive 6x cubed. This should be straightforward. This is positive 2x. Now, that is what you check to the original. See, we did this. We did it. Check it with the original. So does this match the original? No. So the way you would answer this is you would say, not even. And I don't know if you want to maybe come over here and say to yourself, you know, like this does not equal the original. Maybe I changed to a different color. That's how we determined that it's not even. It's not the original function. Now let's check if it's odd. Here's the beauty of checking for odd. I'm going to copy the rule. This is why you want to do it in this order. The rule for checking odd, you're going to have to memorize the rule. It pulls the f of negative x down, and it has to equal negative f of x, which basically means negative y. That's the rule. Now, here's why you want to check even first, then odd. You already found this. I'm making a note here instead of just saying it to you. Making you put it on your paper. You already found f of negative x. Hopefully you found it correctly, but you already found it, right? So all you need to do is to find this. So I'm just like we did up here. Do this. You're doing the latter part of the rule, and you're checking it with the first part of the rule. Well, you already found the first part. It was up here. So we just need to find this. Now, how do you understand this? How do you read it? Negate the entire function is the way you read that. Negate the whole function, which means multiply the whole function through by negative 1. So let's find it. I'm going to come right here because I have no room right there. Negative f of x means negative times the whole function, right? Copy the whole function. 5x to the 7th minus 6x cubed minus 2x. So you're multiplying every single thing by negative 1. Do the exponents matter if you're multiplying the coefficients by negative 1? No, they don't. Are y'all going to be back tomorrow? Yes. Okay. Is it region? Yeah. So this is the function, right? Just hold on, I'm not done with it. Does this match this? Then it has odd symmetry. So I'm going to make a note. I'm changing colors. This is what I found when I negated the whole thing. And it matches matches f of negative x. It does match it. So that means that it has odd symmetry. Good luck, y'all. Hey, here, hold on. So you don't have to search for it. Let's make a note. Oh no, it's on the next example. Go to the next example. Next slide. You'll notice it says number 3B. That's because this had so much writing, I put them on two different slides. So go to the next slide. You're doing 3B. You're checking for even, odd, or neither. Check even first. Makes your life a lot easier. And I find that most people like checking even because it's just plugging the negative x in and cleaning it up. Okay, what's, yeah.
So the odd symmetry, is that, have we done that yet? Is that when we did it? Is that the symmetry in both x and y?
Odd symmetry is
Plugging x and
if
y.
you have an equation that's not a function, it is plugging negative x in and negative y in. If you have an equation that is a function, it's the same concept, but the way that you have to write it, since it's a function, is f of negative x would equal negative f of x. This means your input of negative x will produce a function that's the same thing as a negative y, which takes care of the rule for rotating around the origin, which is odd. That's the odd symmetry. So now y'all are checking this one. Check for even. Remember the rule for even. You're just checking if the function ends up being the same after you plug negative x in. So remind yourself that this is what you're doing. Do this. Of course, this is not F. I wrote F. It's H. Are y'all good with that? Do I need to change the F's to H's? Are you good, Gracie? I thought you were shaking your head like, no, you need to change it. F of negative x. So I'm plugging negative x in. Everywhere there's an x. 5, beep, 6, x to the 6, minus 3, beep, squared, minus 7. I'm plugging in negative x. Don't overthink it. That's a negative to an even, so it's going to come out positive times 5. That's a negative to an even, so it's going to come out positive times negative 3. Copy the negative 7. Is that the same as the original? This equals the original, which means it is even. So this has even symmetry. Now here's a beautiful thing. If it has even symmetry, there's no need to check for odd symmetry. You need to check for odd. it cannot be both even and odd. It can't reflect over the Y and rotate 180. It can't do both. Okay? Yeah, it could be neither. So make a note. It cannot be both even and odd. And the easiest way to remember that is there is no number that's considered both even and odd. I'm about to say 0, but 0 is a controversial number. Don't even get me started on that. I had an argument with my professor in college about it. He says even. He says 0 is neither, and I say 0 is even. Because 0 is divisible by 2, which is the rule of whether a number is even. You told me I was wrong. Huh? He said it was neutral. He said there's like papers and studies and all this, but then I went home and I researched it and I found papers saying it's even. So I was like, ha! No, I think it's just a preference. I say 0 is even because it's divisible by 2. And that's the definition of even, a number divisible by 2. Well, 0 divided by 2 is 0, which means it's pretty, which means it's divisible, which means it's even. And he didn't. That's all right. Last example. Find a point that is symmetric to the given point, negative 5, 6, with respect to the x, the y, and the origin. This is so simple. I wanted to put it on here because I was afraid you would overthink it and make it way more complicated. The first thing I would do is sketch a picture. Sketch a little coordinate plane, right? And plot negative 5, 6 on it. What quadrant is negative 5, 6 in? What quadrant? Quadrant. Y'all better know it. Y'all take my pre-cal, know it. That's quadrant 2. So negative 5, 6, it's probably like right there, right? This is, I'll just make it really big. That's our starting point. It's negative 5, 6. What would the coordinate point, it's asking you to state the coordinate point after you reflect over the x, go back to the original, reflect it over the y, go back to the original, rotate it around the origin. Write the coordinate point that it would produce once you did those reflections or rotation around the origin. Rotating 180. So what point is symmetric to negative 5, 6 with respect to the x-axis? Very good. What point is symmetric to negative 5, 6 with respect to the y-axis? What point is symmetric to negative 5, 6 with respect to the origin? And if you plot those, so like this would be negative 5, negative 6. This one's 5, 6, and then over here is 5, negative 6.